All right, so we're going to start part 2 now. I'm going to take up where I left off here. We're going to talk about when a limit fails to exist. So we kind of mentioned a little bit about does not exist, right? So let's talk about a few different situations in which a limit will fail to exist. So the first part of when a limit will fail to exist, or a DNE, is when the behavior is different from the right and the left, and that's what we talked about in the other video. So for example, let's sketch this function, right? This is that absolute value rational function that we talked about yesterday, and we did this one in the Graph-O-Rama. So you should have this graph memorized. It's a very important graph that's going to come up a lot in these next few weeks. So again, it's an open circle to the right here at 1, and then open circle to the left at -1. Okay? So let's evaluate the limit as x is approaching 0 of this function. We can look at it numerically here. So I look at values to the right, 1, 2, 3, 4, right? What's the y values here? Well, the y value at 1, 2, 3, 4, all these y values are 1. Right? So from the right, I'm definitely approaching 1. From the left, though, it's down here, right? -1, so at -1, at -2, at -3, at -4, the y values are all -1. So from the left, all of these numbers are getting closer to -1. So notice from the right getting closer to 1, from the left -1. And you can see it on the graph as well. From the left, I'm approaching down here -1. From the right, I'm approaching +1. This is a different behavior from the left and from the right. So my left-hand limit is -1. My right-hand limit is +1. So my overall limit does not exist. Since f of x approaches different values from the left and from the right, the overall limit as x approaches 0 of f of x, DNE. Okay, so that should be pretty clear. We've seen that a couple times now. All right, so that's the first situation when you have a does not exist. Okay, a second situation where you're going to have a does not exist is when you have what's called unbounded behavior, meaning it's not bounded or it keeps going on and on forever and ever. Okay, so here's another one we saw yesterday, 1 over x squared. Think about the graph of this one. It's going to look something like this, and then since it's x squared, they're both going up in the same direction. Vertical asymptote at x equals 0, horizontal asymptote at y equals 0. Okay, what's the limit as x approaches 0 of f of x? So I can look at what value is it approaching from the left, what value is it approaching from the right. So we can look graphically, and we notice that it's just getting bigger and bigger. So we might say that it's approaching some sort of infinity, right? It's going to keep going forever and get higher and higher and higher from the left and from the right. Infinity, unfortunately, is not a number. And so the limit has to be an actual number. So therefore, when we get to this infinite limit, that is a limit that does not exist. And I can show it numerically here as well. We can plug in some values, right? 0, 0, 1, 0, 1, 0.1, 1, right? We can do -0.001. And so numerically, too, you can kind of see what's happening here. This is 1, this is 1. Right, and we can look at these. We can type this in our calculator. All right, so there's our 1 over x squared. I can go to my table, -1, -0.1, -0.01. Right, at 0, I'm going to get that error message. Okay. Okay, and so you can see how these values, right, are getting higher and higher. So this is 100, this is 10,000, this is 100, I think, a million, right? And then this does not exist, it's error, right? It's an asymptote. But then, again, we are higher up here. Okay, so again, they're both going higher and higher. We're getting close to what I would call infinity on both sides, but it's not a real number, right? L, your limit has to be a real number. So infinity does not work. So if you ever have it approaching infinity, approaching an asymptote, we're going to talk more about infinite limits in a couple more sections later, but that asymptote idea, this is when you would have a limit that does not exist. All right, the third situation when a limit doesn't exist is called oscillating behavior. Now, this doesn't happen very often, But I'm going to give you an example of a graph where it will happen. It's a sine of 1 over x. This is one where we wouldn't know how to graph this by hand, so we would use our calculator. Sine of 1 over x. And you want to make sure anytime you're graphing a trig graph that you are in radian mode. So double check that you're in radian mode. And then take a look at this graph. So I've zoomed in a little bit so you can see it. Kind of see what's happening in here. It kind of does this big, in the inside here as we get closer and closer to 0, it's doing this bouncing back and forth, and that's really all that oscillating means. So an oscillating function is one that as you're getting close to that value does this, boom, 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 and then it kind of comes back out like that. Okay, so it's this up and down, this quick little jumping back and forth motion on the inside. And if you keep zooming in closer and closer, you can see that on your calculator. So let me give you some idea what's happening with these values. If you type these into your table, what you're going to notice here at 2 over pi, I'm at 1. At 2 over 3 pi, make sure there's parentheses on the denominator, this is at negative 1. At 2 over 5 pi, I'm at 1. At 2 over 7 pi, I'm at negative 1, and etc., etc. And so it's doing this bouncing back and forth. So as I'm getting closer and closer and closer to 0, these numbers are getting smaller and smaller, right? As they're getting closer and closer and closer to 0, it's doing this ping pong, back and forth, back and forth, back and forth. And so since it's oscillating between those two numbers, this is another situation where I would say that the limit does not exist. Okay, so far those are 3 main types of when a limit doesn't exist. Okay, so the first one, different number from the right side than it approaches from the left. That increases or decreases without bound. That's where we're looking at positive or negative infinity, vertical asymptotes. And then this idea of oscillating between two fixed values, bouncing back and forth. These are the 3 situations when you can write DNE. Don't get DNE happy, where everyone just writes DNE, DNE, DNE for all these limits. That actually do exist, okay? So it's pretty specific, the times when you can say a limit doesn't exist. Okay, so it's not that often that you say that, right? So you really got to be specific, and it needs to be one of these 3 situations. That is it for the notes.